Welcome viewers. In this video we are going to do design of a substation gantry foundation using European code. This is stage 1 out of 7. This substation gantry foundation will have more calculation part. So these are divided into various stages. That is 7 stages we had divided. In the first stage we will be looking on overview of this calculation which is prepared in Excel sheet. These are the detail about the various design stages which we are going to look on this substation gantry foundation calculation using Eurocode. First one is a overview of calculation. This is we are going to look in this current video as a stage 1. Followed by that stage 2 we will be looking on foundation and soil parameters, loads and load combinations. Third one is stability check. Fourth one is anchor bolt design. In fifth stage, we will be discussing about the design of bottom pad or bottom slab. In the sixth stage is a punching and one-way shear. And finally, we are going to conclude with this design of pedestal for this entire substation gantry foundation in Eurocode. Let me look into that overview of calculation in Excel sheet. On the screen you can see an Excel sheet which we had developed to design a gantry structure foundation. So this is an overview. In this overview we will be looking at what are the loads and how the calculation is going to work on the stability check, and finally what are the element which we are going to design. So that we will look into this overview of this calculation. So first, when talking about the loads and load combinations, there are three set of loads we need to consider. One is the primary loads. In this primary load, these are the load list. The 10 number of primary loads we need to consider from the structure. That is a dead load without ice, we can consider this as a D, and dead load with ice is a DI. Wire tension at 0 degree deviation we can consider as a T0, and wire tensions at a maximum deviation 30 degree we can consider as a T30. Extreme wind is WE, we can consider WE0. Extreme wind in 45 degree, that is oblique diagonal wind, is WE45. Extreme wind we can consider WE in 90 is a perpendicular wind to conductor span. Similar like high wind also we need to consider the 3 directional or 3 angle wind, 0, 45 and 90 degree. 0 is a parallel to conductor and 90 is a perpendicular to conductor. So always the longitudinal forces are parallel to conductor span. Longitudinal forces means the forces which is in 0 degree we need to consider as parallel to conductor. And high wind is nothing but it is a 70% of extreme wind we need to consider as per EN 50341. EN 50341 part 1 and its national annexure. You can find this explanation. High wind equal to the extreme wind of 70% of the extreme wind to be considered. So these are described in EN 50341. Next, coming to the load combinations, there are two type of load combination. One is a serviceability limit. This will required to check the stability. Second one is a ultimate limit states, ULS. So for this there are various load combination explanation is given in EN 1990. So for service load combinations we need to combine the dead load plus tension, wire tension loads plus the wind load in 3 directions, 0, 45 and 90 degree. 0 is a parallel to conductor again, 45 is a diagonal to conductor span, and 90 is a perpendicular to conductor span. So these are the consideration we need to do. So here the H define the high wind, E define the extreme wind here. Similar like for load combination for ultimate limit states, these are the combinations factor. So 1.35 plus dead load plus one tension, wire tension plus 1.5 times wind, that is extreme wind. So again another three cases are like 1.35 di is a dead load with ice, which we had seen here, and wire tension Ti and 0.9 wind. So here that Ti means wire tension according to the inclination or deviation of angle. Here we had considered two type of wire tension. One is 0 degree deviation, another one is 30-degree deviation. So that I represent 0 and 30. Next one is foundation stability check. So these are the various check we need to consider: bearing check, overturning check, and sliding check. So when we look into that bearing pressure check, we need to check whether the maximum gross pressure derived from the foundation is less than the safe gross bearing capacity. Then we can call it as this foundation is safe with the subsoil. So for that we need to check two conditions. Before that we need to find out eccentricity E of the foundation. So the eccentricity E is nothing but actual eccentricity of the foundation. We need to design as per the moment which is occur at the bottom of the foundation divided by the total vertical load. So we need to calculate this actual eccentricity first in order to find these conditions. Either the bearing capacity formula we need to use as per the condition 1 or 2, that should be decided according to the actual eccentricity of the foundation. So here that E is a moment divided by the vertical load. This E we need to check with the limiting eccentricity. Limiting eccentricity is nothing but the B is a dimension, breadth of the foundation or the length of the foundation, which is towards the moment which we are going to calculate, divided by 6. So if this calculated eccentricity is less than the limiting eccentricity, then we need to go for these first conditions. We need to use this equation to find the maximum actual gross bearing pressure. If the eccentricity is greater than the calculated eccentricity is greater than the limiting eccentricity, then we need to go for condition 2. So this case of equation we need to consider for finding the bearing pressure 2b divided by b into x. So for calculating the x, this is a contact length of the foundation base. We need to calculate as per this formula 3 into 0.5 into L minus E. So E again is a actual eccentricity, and here remaining values like P divided by A. The P is a total vertical downward load from the structure plus weight of the overburden soil plus self weight of foundation in kilonewton, and A is the area, plan area of the foundation. So eccentricity we already seen. So this is actual calculated moment. So this is moment M is a moment at the top of the foundation which is come from the structure plus horizontal force is a H from the structure multiplied by the Y bar. Y bar is nothing but the lever arm distance from the top of the foundation to the bottom of the foundation. So that distance we need to consider in order to find out the moment at the base of the foundation. So this value will help us to find out the actual eccentricity, and the breadth we know. Breadth is a B is the breadth of the foundation, L is the length of the foundation or bottom pad. So M is the moment of structure at the top of pedestal. So maximum eccentricity, the eccentricity E which is calculating should not go more than the maximum eccentricity. So in that case, the definitely that foundation will going to overturn. So we should not go the eccentricity beyond this B by 3 or L by 3. So with that, check for bearing pressure will over. Next one is check for overturning. So check for overturning, in simplify we can say that resisting moment divided by the design moment, that is MRC divided by MED, should be greater than the partial resistance factor defined in European Code EN 1992, sorry, EN 1997. So for that, calculating the moment resistant capacity is equal to P divided P into B divided by 2. So here the B is the width of breadth of the foundation, P is the total vertical load from the structure plus weight of overburden soil plus self weight of the foundation. So by this way we can able to find out the moment resisting capacity of the foundation, and the MED is a design moment at the base of the foundation. This is nothing but where we had calculated here MO equal to calculated moment at the base foundation, which is equal to M plus H into Y bar. So here that Y bar we know M and H are the moment and horizontal forces from the structure. So we can able to calculate this one. So if this condition is applies, like MRC divided by MED is greater than partial resistance factors, then the foundation is stable in overturning. Next, coming to the check for sliding. So here that sliding, again it is a VRC divided by VED. VRC is a sliding resistance of the foundation in kilonewton, which is to be calculated phi by W. W is a total vertical downward load from structure plus weight of overburden soil plus self weight of foundation. Phi is a 2/3 of tan phi. So this tan phi is generally 30° or according to the soil investigation report we need to consider. So that 2/3 tan phi is a value of this coefficient of sliding between soil and concrete we need to find out, and multiplying with that weight, total weight of the structure, weight of overburden soil plus weight of foundation, we will be getting this VRC. And VD is a calculated shear force at the base of foundation. So that is nothing but the H which we had calculated, which we had extracted from the structure. So if it is these conditions, VRC divided by VET, that is resisting sliding resistance divided by design shear, is greater than partial resistance factors, then this foundation is safe in sliding. Next, coming to the design of foundation. So in that design of foundation, there are various elements like design of anchor bolt, design of bottom pad, and finally the design of pedestal. So design of anchor bolt, we need to do two calculations. One is to check for combined shear and tension, which is as per table 3.4 of EN 1993 part 1 section 8. Second one is check for bond length in tension. This will give you how much length of the anchor bolt is required to inside the embed to the concrete. So this we need to calculate as per 8.4.2 class in European Standard EN 1992 Part 1 Section 1. Anyway, this we will be looking in detail about how to calculate this design of anchor bolt using the formula which is described in these two classes and tables. We will be seeing more detail in upcoming part. So design of bottom pad, based upon the net upward bearing pressure, we need to calculate the reinforcement steel for both the direction and both the faces, top and bottom, we need to calculate. So anyway, we will be doing that in upcoming video. Addition to that, we need to do check for punching shear, that is two-way shear. This is as per class 6.4 of EN 1992 part 1 section 1. So this is a plan view of how the punching shear or two-way shear will occur. So this two-way shear will occur from the face of the column at a distance of d divided by 2. So here the d2 is nothing but the depth of the raft or bottom pad. So this red color part is the punching shear development diagram. So if the calculated or actual punching shear is less than the resistant punching shear, then there is no requirement of shear reinforcement, or else we need to provide the shear reinforcement. But this VD should not exceed VRD max described in EN 1992. If that is the case, then this foundation raft is not suitable for the shear. Then we need to revise the size. Either we need to increase the thickness, or we need to try to reduce the length or width of the foundations. So we need to check that criteria. It means that VED should not be greater than VRD max in any case. If it is a greater than VRD, that is resisting shear, then we need to provide the shear reinforcement. So these are the formulas and equation which are given in the European standard EN 1992 in class 6.4. So in order to find out the VED, that net factor punching shear stress at foundation pad, we need to calculate, or we need to get from the structural loads, and VRD see punching shear capacity we need to calculate using this equation. So anyway, we will be seeing this in our upcoming video during this stage of punching shear. So this is nothing but these are the formula are given in European standard. So the partial factor, so VRD equal to 0.18 divided by gamma C K into, so K into 100 PA. PA is a reinforcement percentage, FCK is a concrete characteristic strength, and sigma CP is a normal concrete stress in the critical section. So this is for this cast in situ concrete, this value will be 0. So we can ignore this minus 0.1 sigma CP, and entire this equation should not exceed 0.4 FCTD. So FCTD is nothing but it is a design value of concrete tensile strength in megapascal. So for that we need to calculate using this equation 0.7 into 0.3 into FCK power 2 by 3 divided by gamma C. So likewise we need to find out this. So once after finding this VRDC, we need to check whether it is greater than VED calculated or actual punching shear. If it is greater than the VED, then no need of providing any shear reinforcement. So this is the equation to find the VRD max, that is maximum punching shear carrying capacity of concrete. So 0.5 V FCD, V equal to 0.6 1 minus FCK divided by 250, and FCD is a design compressive strength in megapascal. So these are the formula to find out FCD. 0 alpha CC into FCK divided by gamma C. Alpha C is nothing but 0.85. So these are the equation already given in the class 6.4 of EN 1992 part 1 section 1. Anyway, we will be looking this in during our detailed calculation. So this is just a overview in this stage. And the next one is a check for one-way shear. So this should be checked as per class 6.2.2 of EN 1992 part 1 section 1. So here VED1, that is one-way shear, should not greater than the VRD CT, so that no shear reinforcement is required. So in order to calculate this VED, we need to get from the maximum factored shear stress at foundation pad. This is as per structure forces. Then VRD, that is resistant one-way shear, we need to calculate as per the above equation in here, VRDC. So if this equation satisfied, then no shear reinforcement is required. So next, coming to the design of pedestal, here we need to do only mainly two checks before going for a reinforcement design. One is either this element is a pedestal or column. For that minimum lateral dimension, if the height divided by the minimum lateral dimension L or B, L and B are the lateral dimensions of the pedestal or the column. If it is less than the 3, then this element should be designed as a pedestal, or else if it is a greater than 3, then we need to design this as a column, that is a cantilever column fixed at base with the bottom pad subject to bending and axial tension and compression. So this criteria we need to check first. If it is a pedestal, then we can provide a nominal reinforcement around the pedestal and with some lateral ties which is required for the shear resisting. So there is no calculation is required for that. But in case the depth divided by the lateral least lateral dimension is greater than 3, then we need to design this as a bending axial loaded or axial tension or compression plus bending kind of equation. There is a chart in European standard. We need to calculate this. Anyway, we will be looking this in our detailed video explanations. Second one is we need to check the slenderness also. So anyway, that detailedly we will be looking in our upcoming videos. So with this overview of the calculation get completed. So we had seen so far the loads and load combinations, foundation stability checks in bearing, sliding and overturning, and the design of various foundation elements such as anchor bolt, bottom bed and pedestal. So we will look more detail about all this, how these stability checks are performing and what are the loads, load combinations which we got considered. So this detail we will be explain, we can able to see in our upcoming video. Thank you. Look description for more related videos. Subscribe to this channel for more updates. Thank you.